In this video, we're going to work problem number 3 from Practice Exam 3-1 in the fall 2021 semester of Chem 12-11. And the problem here is deceptively simple. Our goal is to identify the highest energy orbital from the choices below, assuming that all orbitals are unoccupied. And this is potentially important later. Now, what in the world are we looking at in terms of the choices here? Well, I've got N, L, and M sub L values, and each one of those corresponds to an orbital. These are quantum numbers, and so I should be thinking in terms of quantum numbers for this problem. The constraints on quantum numbers, and especially how they relate to the energy of the orbital. Now, one thing I like to do when dealing with quantum numbers, because my brain abhors numbers, is to convert each of these into a subshell label and think about the subshell labels. These are things like 1s, 2s, 2p, 3s. These labels, in my experience, are easier to remember and easier to deal with and think about than sets of quantum numbers like this. So let's go ahead and do that for the 5 possibilities. So A is n equals 2, L equals 1. That's going to be a 2p label right there. B is 4, 0, 0. That's going to be a 4s label because L equals 0 corresponds to S, L equals 1 corresponds to P, so on and so forth. C is going to be a 3s subshell. D will be a 3p subshell. N is still 3, but L is now 1. And that last choice there is going to correspond to a 3d subshell. So there we have it. Now we have subshell labels for all 5 orbitals, and we want to know which of these subshells is highest in energy. One point to note here as well, which is another advantage of using the subshell labels, is we haven't looked at M sub L at all, and that's because M sub L is irrelevant. We're interested in the energies of these orbitals, and orbitals with the same values of N and L, but different values of M sub L are equal in energy. They're degenerate, right? So we actually don't even need to care about the M sub L values provided, as long as they make sense in terms of the rules of quantum numbers, which all of these do. So that is worth checking. We won't do that here, but that is worth going through and double checking as you're solving a problem, say, on an exam. Now we're interested in the relative energies of these, and we need to think back to the rules for quantum numbers and how they relate to energy. And one thing that we should note right away is that the higher the value of n, generally speaking, the higher the energy. So generally, n equals 1 is lowest, n equals 2 is next, and then 3, 4, and 5. However, we also know that within a shell, the energies of the subshells increase s to p to d to f. And when we get to n equals 3, 4, and 5, there can be some intermingling between these various energies. So let's use these ideas and try to arrive at the highest energy subshell here. So just to avoid confusing us, I'm going to erase this note about higher n, higher energy, because we might see some intermingling. What that does allow us to do immediately, though, is rule out 2 things that are definitely not highest in energy. The 2p subshell, which is lower in energy than most of the other orbitals. In fact, that is the lowest of them all. And then the 3s and 3p cannot possibly be higher in energy than the 3d orbital, because those are all within the n equals 3 shell. So that leaves 4s versus 3d. And here's where assuming that all orbitals are unoccupied comes in to play. When the orbitals are unoccupied and electron-electron repulsion is not an issue, the 3d orbital is actually higher in energy than the 4s orbital. And this, for example, we can surmise from the periodic table, where the 3d subshell is filled after the 4s subshell. So scandium is the first element that has a 3d electron, and it is 3d1. Calcium, that comes right before it on the periodic table, is 4s2 with no d electrons at all. And that, combined with this important note that we should assume all orbitals are unoccupied, tells us that under those circumstances, the 3d orbital will be the highest in energy.